In this lesson, we begin to look at the concept of electromagnetic waves. So before this, we've talked this semester so far about electricity, electric fields. We talked about magnetism and magnetic fields. And we talked about wave phenomenon in the last class in Physics 141 toward the end of the semester. Well, James Clerk Maxwell, probably one of the most brilliant theoretical physicists to have ever lived, took all of the work done by Michael Faraday and Ampere and other contemporaries and organized it together in a set of 4 equations that revolutionized our understanding of electricity and magnetism. So these are called Maxwell's equations today. Even though Maxwell himself only actually really worked on one of the equations, he was the first to put them together and show the symmetry that exists between electricity and magnetism. That a changing electric field generates a magnetic field, and a changing magnetic field generates an electric field. So, since he was the one to put all of these together, he is the one credited with this discovery and understanding. Now, the equations themselves are beyond the scope of this class. They require integral calculus or vector calculus to really be able to understand them, so that's beyond the mathematical scope of this class. Just know that James Clerk Maxwell revolutionized our understanding of electromagnetic theory by finding the symmetry between electric and magnetic fields. His equations also led to the prediction of what are called electromagnetic waves. Like I said, a changing electric field can generate a magnetic field. But if you're generating a magnetic field, you're changing it. And a changing magnetic field generates an electric field. But if you're generating an electric field, you're changing it. So what actually happens in an electromagnetic wave, it's a self-propagating electric and magnetic wave. The electric field oscillates with time and the magnetic field oscillates with time, and this wave propagates through space. We'll learn that, unlike other mediums like sound medium or earthquakes, light itself doesn't need a medium to propagate through. Light can actually go through, or electromagnetic waves can actually go through the vacuum of space without a problem, whereas sound waves can't. Now, we know that visible light is an electromagnetic wave. The light that you're seeing me with right now from your monitors, if you're viewing it, that light is a wave. Unlike the sound waves where you're hearing me, for those of you who are, have the sound turned up and can hear me, that's a sound wave. That's a different type of wave. So the electromagnetic waves create what's called the electromagnetic spectrum, which we'll look at in more detail in the next video. And visible light is a small fraction of that spectrum. So light that we see above is actually an electromagnetic wave. It wasn't known for a long time what light was. Early thoughts were that light actually came from beams from the eyes that reflected off of objects and came back into the eyes. That's not easily disproven if you've ever walked into a dark closet, right? If our eyes are the source of the light that we see, why can't we see in a dark closet? Because our eyes are still there. So electromagnetic radiation is generated by lights, by the sun, by hot objects, and allowing us to see these objects. Now, in a vacuum, we will learn, electromagnetic waves, using Maxwell's equations, Maxwell predicted the speed of an electromagnetic wave to be about 3 times 10 to the 8 meters per second. That's what your book gives, 3.00, I believe, times 10 to the 8 meters per second. The exact version, so speed of light is 1 over the square root of the permeability of free space and the permittivity of free space. Although I might switch those around. The speed of light, when you plug this in using the values as precise as we know them, comes out to 299,792,458 meters per second exactly. In fact, the length of a meter is defined so that number comes out to be exact. Incredibly fast. Unlike sound waves, which travel several hundred meters per second, light waves travel much, much, much faster, which is why it was so difficult to measure the speed of light in early experiments. And it wasn't until Ohmler, I believe, Danish astronomer, measured the speed of light within about 10% in the late 1700s, early 1800s, I believe. Hertz. Now, going from Maxwell, your book jumps to talking about Hertz. Using Maxwell's equations, people realized that you can transmit and accept and detect electromagnetic waves. So Hertz was the first physicist to actually play around with electromagnetic waves in that he could send out an electromagnetic wave and detect it. This was the beginning of a revolution, right? Modern radio came about from the work that Hertz had done. And today we use this, it's ubiquitous, right? We use this technology almost daily in our lives. If you have satellite television, you're getting an electromagnetic signal from a satellite orbiting the Earth. If you have a cell phone, your cell phone is communicating with a cell tower via electromagnetic waves. Right? If you have Wi-Fi, if you're watching this on your laptop with a Wi-Fi connection, your laptop, your desktop, if it's Wi-Fi, your cell phone that's Wi-Fi enabled, all of those are communicating via electromagnetic waves. So this type of technology has become really critical for modern technology. It allows for wireless transmission of signals. I mean, modern television, actually modern television is mostly cable TV now, but back in the 70s, 80s, right, you would actually send, big broadcast towers would send electromagnetic signals out into space. An antenna on your roof would detect it and allow you to watch television. So a lot of work was done over 100 years ago at the beginning of our understanding of what electricity and magnetism is. And we will look in more detail about these electromagnetic waves and investigate what's called the electromagnetic spectrum next.